Okay, let's do the Gram-Schmidt process. Now that we've completed projections, so on to section 6.2. This is why you did projections. Arguably why you did dot products. Dot products were useful for finding angles. Dot products really tell you something about projections. Way back when we first did dot products, I might have mentioned, here's what they're good for. They're good for projections. Well, let's make some additional sense out of that. In the previous section, and I word this, we expressed a fondness for computational simplicity for vector spaces with bases that involved pairwise orthogonal unit vectors. Projections then are a piece of cake. If we've got orthogonal vectors that are unit vectors, when you compute those projections, it's a bunch easier. So the plan in this section is to run with that idea of projections and projections onto subspaces W and their perp spaces, W perp. Use these ideas to produce a nice basis from a not so nice basis. By nice basis, I'm thinking orthogonal unit vectors. Not so nice, I'm thinking not orthogonal vectors. The unit part, I could, that we could cope with a little bit better. The orthogonality part is quite convenient to have. The unit vector part's convenient too, but it's harder to live without orthogonality. This can be a little lengthy in terms of computations when we go through this process. All right, well, let's get the ball rolling on what I like. I like orthogonal unit vectors. First, for orthogonal, a set of vectors, v1 through v sub k, non-zero vectors, in Rn is said to be orthogonal if the vectors v sub j are mutually perpendicular. That is, if v sub I dot v sub j equals 0 when I and j are different. We have never defined this before. We defined two vectors being orthogonal. Here we're defining a set of vectors as being orthogonal. So that's why this is new. Well, it just means every pair of the vectors in the set are orthogonal. So not a surprise on that. I like orthogonal vectors and I like unit vectors. So one step at a time. Let's look at theorem 6.2, which says, suppose you have a set v1 through v sub k of orthogonal vectors, orthogonal non-zero vectors in Rn. Then this set is independent and consequently is a basis for the subspace it spans. So orthogonal vectors are linearly independent is the claim from this. Let's look at, here we go, a proof of that for one reason. It's not terribly long. All right. Let J be some number between 2 and K. We started with K vectors. All right. We're going to take the first J minus one of those vectors. If J equals 2, we're taking a single vector. If J equals 5, we're taking the first 4 vectors. Let J be an integer between 2 and K, and consider the equation v sub j equals s1v1 plus s2v2 up through s sub j minus 1 v sub j minus 1. It's a linear combination of the first j minus 1 vectors. And we're trying to write vector v sub j as a linear combination of those first j minus 1 vectors, something that you won't be able to do if these are linearly independent. So that's how the argument will go. All right, suppose we had this type of linear equation. If we took a dot product of each side of this equation with vector v sub j, then we're going to get nonsense. V sub j dot v sub j, that's a norm of v sub j squared. So do a dot product with v sub j on the left-hand side of the equation, you get the norm of v sub j squared. That ain't 0, because v sub j is not the 0 vector. If you do the dot product on the right-hand side, we'll get v sub j dotted with this, scalars pull through. We get S1 times V sub j dot V sub 1. What do you know about V sub j and V sub 1? They're orthogonal. It's an orthogonal set of vectors. So V sub j dot V sub 1 is 0. V sub j dot all these things is 0. So we're getting not 0 on the left and 0 on the right. That can't happen. You can't have this equation satisfied. So that's how the argument goes. Here's the verbiage for it. Take the dot products. You get 0 on the right-hand side. On the left-hand side, you'd get the norm, which would imply that the dot product of V sub j with itself is 0. It's not the 0 vector. That's a contradiction to the assumption that there exists such an equation. So you can't have any V sub j as a linear combination of its predecessors. We've mentioned this in passing, I guess it's page 203, number 37, that when you have that kind of behavior, you have a linearly independent set of vectors. So we're putting some weight on this exercise from out of the book. But we have mentioned writing a vector in terms of the linear combination of its predecessors in one of the earlier proofs. So the punchline here is orthogonal vectors are linearly independent. In the notes, they even said something about a basis, didn't they? Consequently, you can take that set of vectors as a basis for the subspace, which they span. What's a basis? A linearly independent spanning set. Well, we just saw the linear independent stuff, so let's consider the span stuff. So consider the subspace of Rn, which these vectors span. It'll be a basis for it. I mean, it's going to span it because that's the space we're considering. They'd be linearly independent because we just showed they're linearly independent. So orthogonal vectors are linearly independent. You like linearly independent vectors. Got into all this linear dependence, independent stuff with an idea, maybe somewhat of an idea of direction. Also an idea of, geez, when I've got a linearly dependent set, there's some redundance in that set. I don't need all these vectors with an eye towards taking linear combinations. I've got extra vectors when we addressed whether sets of vectors were linearly independent by looking at column spaces and doing row reduction stuff and counting pivots. I'm looking for pivot-free columns, which I think about in terms of systems of equations with free variables and multiple solutions. There's some sort of extra stuff, it seems, involved in this when we don't have linear independence. All right, so what we want to do is find a projection of a given vector B on a subspace W, like we did in the previous section. The way we did it before, we had to find a coordinate vector relative to a certain ordered basis. Well, we still have to do that, but if we've got an orthogonal basis, it's a whole bunch easier, as the following theorem claims. All right. So take vectors v1 through v sub k to be an orthogonal basis for some subspace W of Rn. We want to take vector b from Rn and project it onto this subspace. All right. Claim is that projection can be found by these computations. All right. Now, if you recall how we did this before, we had to have some basis for W, or find a basis for W. Usually in the exercises, they gave us a basis for W. Then you had to turn around and find a basis for W perp, which involved finding the null space for a certain matrix. Here, there's no mention of W perp. So you ain't got to deal with W perp. Yeah, but here, you've got not just a basis for W, you've got an orthogonal basis for W. All right, so let's go through the proof of that one. I guess one of the observations is you project onto this subspace W by projecting B onto the first basis vector. So subscripts are pretty small. Projecting onto the first basis vector, that's what this is. Projecting B onto the second basis vector and the third basis vector up through the kth basis vector. Those projections, piece of cake, those are just dot products. And you're good at dot products, ain't you? That's why this is a good thing. Orthogonal bases are good. Projections are a piece of cake. They just involve dot products. They don't involve, they're going to find a basis for W, they're going to find a basis for W perp, they're going to find a coordinate vector and chop it off at a certain point. Orthogonal bases, this is a whole bunch easier. Okay, so proof of that. All right. Okay. Here's the claim. We know from Theorem 6.1, it's the thing that told us how to take vector B and deal with it in terms of a component in a subspace W and a component in W perp. We know B can be written as B sub W plus B sub W perp. B sub W is the projection of B on W. In fact, that was our definition of projection on W. And B sub W perp is the projection onto the perp space. All right. Well, we know a basis for W, so we should be able to write the B sub W, vector B, the projection of B onto W, as a linear combination of those basis vectors. After all, B sub W is a vector in subspace W, and these guys here, V1 through V sub K, they're a basis for that. Well, they're an orthogonal basis, better yet. But simply being a basis tells us we can write B sub W as a linear combination of V1 through V sub K with some coefficients, some scalars R1 through R sub K. All right, let's go find those scalars. They're supposed to turn out to be these dot products we've got here. Okay, first, let's take a dot product of vector B with each of the V sub i's, those orthogonal basis vectors. Vector B dot V sub I, vector B, you know, you can write in components like this, dot it with V sub I, use your distribution property of dot products. All right, we just saw we could write B sub W as that particular linear combination because we had a basis for that subspace W. So we'll write B sub W as R1 V1 plus R2 V2 plus dot 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 R sub K V sub K. Take that, dot it with V sub I, use a distribution. Okay, so that'll give us replacing, substituting for B sub W, its linear combination from the previous slide, then taking the dot product and doing the distribution. Here, we've got B sub W perp dot V sub I. Claim is that's 0. V sub I is in W. It's a basis vector for W. And B sub W perp is in the perp space. So the dot products are 0 because these two vectors are orthogonal. So there's neat geometry behind it. And what we got here, when we take these dot products, V1 dot V sub I, well, that's 0 unless I equals 1. V sub 2 dot V sub I, that's 0 because those vectors are orthogonal. Well, unless I equals 2, and so forth. So what you get from these dot products is a bunch of zeros. The only time you don't get 0 is when the R sub something, V sub something has the same subscript as the V sub I. So we've chosen to fix a V sub I here. So we'll get a bunch of zeros somewhere over here in the ith position. We'll have R sub I, V sub I, dot V sub I. Now that dot product ain't 0 because these were assumed to be non-zero vectors. All right, so we were looking for those coefficients R sub I. Well, here's a little equation. Solve it for R sub I. Keep an eye on what's numbers and what isn't. Actually, that's a number because it's a dot product. It's a product of numbers, scalar R sub I, and the dot product of these two vectors, which is a number, a scalar. So we can divide both sides by the dot product, solve for R sub I, and get R sub I equals vector B dot vector B sub I divided by this particular dot product. You didn't divide by 0, right? Right, we were told those vectors were not 0 vectors, non-zero orthogonal vectors. So we found that R sub I is in fact this. Multiply it by V sub I to produce this, and that's exactly what the claim was. So we get that linear combination to be a combination of these things as I ranges from 1 to k. Peek back at the statement. Yeah, that's exactly what we've got. I equals 1 produces this. I equals 2 produces this, up through I equals k. And so we've got B sub W expressed as a linear combination involving nothing but dot products. Notice the pattern with the subscripted i's. It's exactly what we had on the previous page. So if we want to actually do one of those projections, with a piece of cake. It's a pile of dot products, but dot products are easy if we have an orthogonal basis. So let's look at number 4, back to the supplements, where they say, consider W as a span of these 3 vectors, verify that those vectors are orthogonal, and find the projection of vector B onto that subspace. So we got what, a 3-dimensional subspace of R4 because 4 components, 3-dimensional because 3 vectors. They linearly independent. If they're orthogonal, they are. That was the first result we showed. Okay, so let's first confirm orthogonality by taking a bunch of dot products. Is the first one orthogonal to the second one? Let's take a dot product. Do the arithmetic, you get 0. Yeah, first and second one are orthogonal. Let's take the first and the third one. Dot product, you get 0. First and the third one are orthogonal. Is the second and the third one orthogonal? You take a dot product, yeah, you get 0. You really have to check all of those? Yeah, you're in 4 dimensions, and some strange things can happen in 4 dimensions with 3 vectors. You have to check all of this. All right, so each dot product is 0. So these really are an orthogonal set. So we have an orthogonal basis for subspace W. So if you want to project vector B onto subspace W, all you got to do is a bunch of dot products of B with those 3 basis vectors. Okay. The theorem we just stated said this projection will be computed exactly with these coefficients, B dot V1 over V1 dot V1 times V1, and then similarly with V2s and V3s. So it's a bunch of dot products. So straightforward, it's arithmetic. But when we do the dot product stuff, B, here's vector B, here's V1, there's V1, 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 B, V2, 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 B, V3, 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 V3. Notice these coefficients will be number divided by number. So there's scalar coefficients. Over here we got the vectors. So all this stuff here is coefficient stuff. It's dot product stuff that's given above. And you do the arithmetic, and it looks like we get 0, 0, 3 for the projection of that vector B onto this subspace W. Quick observation. If those had been unit vectors, look what you're getting in the denominator. You got V1 dot V1. That's the norm squared of V1. Norm squared of V2, norm squared of V3. Should have a 3 here. If those were unit vectors, we wouldn't have to even worry with these denominators. Now, if they were unit vectors, the arithmetic might be a little bit more awkward. The components would probably involve square roots more likely than not. If we had unit vectors, we wouldn't even have to worry about those denominators. They'd all be 1 if we had unit vectors. And that's where we're headed in the Gram-Schmidt process. Okay, and that's actually the next observation. It says, let W be a subspace of Rn with basis Q1 through Q sub k for W, and we're defining orthonormal. So orthonormal basis if Q sub I dot Q sub j equals 0 for I not equal to j. So those vectors are pairwise orthogonal. So this is an orthogonal basis. And Q sub I dot Q sub I, that's the norm squared of Q sub I, equals 1. Those are called unit vectors. So this is a basis of unit vectors, which are pairwise orthogonal. That's an orthonormal basis. We've used the word ortho a bunch for orthogonal. Normals popped up in passing. We've normalized vectors before. We did it, was it just in the previous section? We normalized the vector to use it for its direction, in a sense. Yeah, we did that with the projection stuff. So ortho for the orthogonal part, and normal indicating that the length has been normalized. They're length 1 vectors. As commented, from what we had above, if we had an orthonormal basis, then v1.v1 would be 1. v2.v2 would be 1. All those denominators would be 1. And we could compute projections just by taking the dot products in the numerators. So if we wanted to project vector B onto subspace W, and we were given an orthonormal basis for W, the computations are simplified a little bit more. So we commented about computationally desirable earlier. Certainly the orthogonal part is desirable because we never had to touch the space W perp. This was all done internally, internal to subspace W. When we had an orthonormal basis, we had to do even less computations involving the dot products. Yeah, if you're given an arbitrary basis for a subspace B, then it becomes a good deal more involved. And we've done plenty of that. I want to write B as a linear combination. Okay, off to the races. It's solving a system of equations. We've seen something like that recently. Let's end the video there, and we'll pick up with a part 2 when we actually get to the Gram-Schmidt process.